today's we have our expert Kuldeep Singh. He is a research scholar and already he had taken a lecture. So I think no introduction is required for him. So today he will be just giving you an insight on the MATLAB modeling side, where how to generally start with a MATLAB modeling. What are the ratings you have to fix on this, and how we will design a grid or something like an electrical power system, and how will we add generators to it. So then how to add an inverter, because an inverter is surely required whenever a renewable energy source is there. It may be in the form of a DC, it may be a wind, it may be, say wind also, what you do, you just convert into AC to DC, and then only again you give it to an inverter and connect it. So if it is a fuel cell, wind or PV, anything, you require an inverter. So he will just give you an insight of all these things, how to connect a inverter to a grid, or how to design it. All those portions will be covered by him. And I just hand over the session to Kuldeep.
Good morning, everyone. As you already know, my name is Kuldeep Singh, and I'm a research scholar here. Past 2 days ago, we have discussed about how can we connect our EV system, electric vehicle system, to the grid system, and what are the components that is required in that in making an EV system. Today, we are going to connect our EV system to the grid. Okay, last time we have only discussed EVs. Today we are going to discuss how can we connect our EV system to the grid. As you already know, EV system is a DC bank system, right? So if we connect a DC source along with the inverter circuit to connect to our grid, that it can also be considered as we're connecting the EV system to our grid system. All right. So today we are going to discuss the MATLAB simulation of our electrical power system, in which we're going to develop three-phase system with RLC load, and then we are going to connect our synchronous generator or asynchronous motor that are present in our system or in the grid as a load, and then we are going to connect our inverter system to that system. Okay, so I have divided these are the objectives of today's discussion. The first one is to creating a simple three-phase RLC model, in which we are connecting with first of all we are connected with RLC branch. Second, we are connected with RLC load. Then we are going to add our linear transformer, two winding linear transformer, and then we are going to see how what's the problem associated with our non-linear type transformer when there is hysteresis present in our transformer. Okay. The second one is creating a three-phase system with the electrical machine. In this, first we are going to model a synchronous generator first. Then we are going to initialize the generator, connecting. Then we connect it to the grid. Then we measure power of grid. Then adding an induction motor as a load in that. Okay. In the third phase, we are going to create an inverter for three-phase load, in which we are converting DC to AC. Then adding PWM generator in that to provide pulses or gate pulses to our inverter. Then we add filter circuit in that inverter circuit, analyzing that filter circuit. Analyzing means we are going to see what are the harmonics present in our signals. Then we are going to make rectifiers, and how we can model the transmission line losses present in our lines, and how we connect these transmission line losses to our current circuit. So this is a simple three-phase RLC model. Okay, and this is the objective, in which we are connecting a three-phase source with a three-phase RLC load, and along in all of this we are connecting a three-phase transformer, two winding type. Okay, this is the circuit we are going to create. So first of all, we are going to create a simple three-phase RLC model with three-phase RLC branch. Okay, in this we have a three-phase source, then a three-phase RLC branch for the transmission line. Like even though we have to connect the three-phase source with the load, in between there are wires that are present. So for that wire we have to account for our RL resistors, inductance and capacitance present in those lines. So we are connecting a three-phase series RL branch, and in the output side we are connecting a capacitor. Okay, this is just a model for three-phase RLC branch. Okay, then in the second, in this these are the parameters we are going to take in order to develop this circuit. The electrical source parameters are the voltage we have taken is 13,800 volt or 13.8 kilovolt. The source resistance, that means the resistance present in our electrical sources, that is 1 e raised to power minus 3, that is 0.001. Okay, that much ohms resistance is present in our source. Similarly, the source inductance is 1 e minus 6, and base voltage is again, these are the parameters that we have to feed in our model. And similarly, the simulation time is 0.1 second. RLC branch parameters are, first is RL branch, what is the resistance and inductance, and then the capacitance branch parameter. Now I'm going to show you this in our MATLAB simulation file. As you can see, this is our same circuit is there. So in this, as you see, we have power GUI and three-phase source, three-phase RL branch, three-phase VI measurement, and three-phase series C branch. I'm using 2016 MATLAB. Okay, so in this, you just have to click in the empty space and write like three-phase source. Okay, the when you write, there is an option coming, the three-phase source that is present in specialized technology fundamental block electrical sources. All right, if you click this, as you will see, a face-to-face VRMS is demanding what's the value it, but leave it as it is. And as you can see, the three-phase source is exactly like that we have used. Okay, if we double click it, then you can see the phase voltage, face-to-face voltage, as we have already, as I've already shown, it should be around 13,800, right? Similarly, the source resistance, that is 1 e minus 3, okay, and 1 e minus 6, and again the base voltage is 13,800. Bye and okay. Similarly, if you want to connect a three-phase RLC branch, just type three-phase RLC branch. Okay, in this, as it is shown, it is saying three-phase parallel RLC branch, three-phase parallel RLC load, then three-phase series RLC branch, and three-phase series RLC load. These are the four options it's giving. So we need a three-phase series RLC branch. So this is the three-phase series RLC branch, third options. And as you can see, when we connect it, so this is a three-phase RLC branch, and we just have to connect it like this. Okay, in the below circuit we have already connected all the system, so you just have to make this whole system and type the values. Okay, when you connect all this system, as you will run it, and in the last slide of our presentation I have already write down all the commands or all the block and their path. Okay, so if you want to connect your system through MATLAB library, okay, so in this system we have a Simscape here. In coming on to Simscape, we go for power system. Then in power system we go for specialized technologies. In specialized technology we go for fundamental blocks. Okay, if we go in fundamental blocks, there are electrical sources present. Yes, three-phase source is there, right, and DC voltage source is also there. When you go for elements, in elements you can see the three-phase RLC branch, series RLC branch, parallel RLC branch, and also there's load are also present in the same block system. Okay, same library. Similarly, if you want to connect the machines, these are the machines present that we are going to connect in our system. And in the measurement block we have a three-phase VI measurement as there is present in our model, and also the multimeter is also there, voltmeter is voltage measurement device is also there, impedance measurement device is also there, and current measurement device is also there. So we are going to use voltage measurement device and a three-phase VI measurement device along with multimeter in our model. And in power electronics, we have universal bridge. And most of the time, we are going to use universal bridge. If you are not don't want to use the universal bridge, you can make your own inverter circuit or rectifier circuit using the above present devices like diode, thyristor, GTO, IGBT, idle switch, and detailed thyristor. You can make your own inverter circuit or rectifier circuit by making or joining this component in a particular design. Okay, so this is the whole system that we have made. This is a simple three-phase RLC system. Similarly, if we go for another system, let's come back to this. These are the parameters they have and that I've given to our model. Similarly, if in the second system we are making a three-phase RLC model with three-phase RLC load. In this case, we have connected three-phase source along with three-phase series RLC load. Okay. As I already told you, the three-phase RLC load is also present in the same library where the three-phase RLC branch is present. Okay, and we have connected a three-phase measurement device in this circuit along with multimeter. Here the function of multimeter is very simple. Let's open that model. Let's say this is a model. Okay, in order to calculate the measurement impedance, you can connect a impedance device that is present, that is impedance measurement device. And if we don't want to connect the three-phase VI measurement device, okay, three-phase measurement device we have seen this one. If you don't want to connect this circuit to calculate the voltage value, current value, or impedance value, you can connect a device like this: three-phase RLC branch connected to three-phase C branch along with impedance measurement device. Okay, in this case, if you double-click this three-phase series C branch, in the measurement it has shown it is taken branch voltages. Okay, so as we have selected the branch voltage in the measurement, these branch voltages will come in this multimeter current. Okay, the multimeter will check for the number of measurement you have put in these blocks. For example, as seen, the C branch contain the three-phase voltages. So the UB1, UB2, and UB3. Okay, these are voltages. And similarly, in this circuit, we have gone for branch current for three-phase series RLC branch, right? In this, we have gone for measurement branch current. So, as you can see, there will be three currents: IA, IB, IC, and the capacitance branch, the three-phase series C branch is providing three voltages: VA, VB, VC. Okay, and these multimeters have chosen which measurement value they have to show. Okay, so first multimeter have chosen the voltages and the second multimeter have chosen the current IB1, IB2 and IB3. Okay, and it is given to the scopes. Most of the time we don't know how to make it the scope with two inputs. Double click it. This is a right. This is a configuration properties. Click it, and in this the number of input ports, make it 2, or as per requirement you can make it 3, 4 and 5. And the moment you make it 2, you want to show your result like this in the matrix form, right? It's a 2 by 1 matrix. So go for the layout, and then in the layout just go for this one, 2 by 1 matrix. And the moment you go for this one, this is how it will represent. If I make it 3 and the layout is like this and apply it, you will see this is divided into 3. Okay, so as per your requirement you can make it 2 or 3 or 4. All right, This was the circuit. If you run this circuit now, in this what we have done is in the three-phase VI measurement, we have taken the voltage measurement as phase to phase, okay, rather than phase to ground. So it is giving us line voltages. And similarly, in the three-phase RLC load, we have taken it as Y grounded configuration parameters, and we have taken branch voltages. Branch voltage matlab VA, VB, VC. So this is giving us phase to ground voltages, the three-phase RLC load, and the VI measurement is giving us phase to phase voltages. That means line voltages. So if you run this whole system, go for scope, you will see this system. Okay, the one is going for the first one is giving the phase voltage, and the second one is giving the line voltages. Okay, as you can see, line voltage is root 3 times the phase voltage. If you multiply this whole system with root 3, you will get about 2 into 10 to the power 4. Your maximum peak will go up to that point. All right, so this is our how to make a three-phase system with RLC block, RLC load. So in the next, we have to add a two-winding linear transformer to the current three-phase RLC system. So in this, we are going to connect a three-phase transformer with Y-Y connection in the whole system with our three-phase RLC load. And in this, why we are doing this? Because of if our load is having a voltage rating of different value, then we have to connect our three-phase transformer, because the generator is of 13,800 volt, and if our load is 2400 volt, what should we do? Then we have to connect a transformer. So this is the same thing we are going to do in this circuit. So let's see in the open, and this is transformer. So just we have connected. In the previous, we have developed three-phase source with three-phase VI measurement and three-phase RLC. In between three-phase VI measurement and three-phase RLC load, we have connected a three-phase transformer. Okay, you already know where it will be present. Transformer in the element department. Okay, so if we run this program again, or first of all, what we have to do here is double click it. If we want to make a phase shifted type, okay, there is no phase shift right now because both the windings are of star type. But if you want to make phase shift, what we will do, make the second winding as delta 1, a delta 11. Okay, it will provide the phase shift 30-degree lag or 30-degree lead, right? So
it will have all this 0, 11, 6 and
no, it only has D1 and D11. In the configuration parameter, there is only D1 and D11, okay? And the last, as you can see, right? So we have taken Y ground, and in the parameters we will given the values of our windings. So let's say our nominal power is 100 e to the power 6 and 60 hertz, and the winding one parameter is 13,800 volt, and the second parameter is 2400 volt. Okay, so it's a 13,800 by 2400 transformer. Okay, 13.8 kilovolt to 2400 volt step down transformer is there. So if we run this program, you will see that the V phase load, that is the voltage present at the load side, is about 2000 volt. Maximum value is coming at 2000 volt, because some of the voltage will be dropped between those lines when coming up to transformer to our RLC load. So little bit of voltage will be wasted there, and our RLC load will have up to 2000 volt maximum. And this is three phase sorry, source voltage, which is up to, we have already know, 13,800 volt. So it has shown in there. So as we can see how to connect a three-phase RLC load which have different voltage parameter to the three-phase RLC source using a linear transformer. Similarly, if we don't have linear transformer, okay, we want to add a parameter like saturation or hysteresis loss. So what we have to do is there is a non-linear circuit is there. This is same as the previous one, just the three-phase transformer with two winding is not linear. As you have seen, there is a line in there which is telling us it's a non-linear transformer. If you double click it, how to make a simple linear transformer into non-linear type? You just have to take that in the type section there is three single phase transformer. In the next there is a simulate saturation. Okay, if you click it, then the option of simulate hysteresis will also come. Okay, let me show you like this. This is a normal linear transformer. Okay, click it, simulation saturation, then we have simulate hysteresis and specify initial fluxes. We are not specifying initial fluxes, we are specifying only simulate hysteresis. Okay, if you go there and go for power GUI, okay, in the power GUI go for tools. In the tools we have hysteresis design. Okay, in power GUI we have hysteresis design. Can click it to the hysteresis design and it will provide you a hysteresis loop as per your requirement or the design of your transformer. They have also provided you with the hysteresis loss sheet. Okay, you can adjust any amount of parameter here and then save it. Okay, the moment you save it, in the it will save as hysteresis.mat file as written over here. Okay, and your circuit will look like something like this. And if you run this, a plot will is coming between flux and current because we have connected this circuit also, the below circuit, multimeter with SI to PU, and flux versus current graph will become. And in this scope circuit we can see, because of saturation or because of hysteresis, the waveform is deforming in the RLC load, right? Because in the source no hysteresis was present, but after it connecting with the non-linear type transformer, hysteresis are present and our waveforms are coming distorted because of hysteresis. So this is the way to connect a three-phase RLC load using non-linear type transformer. So we have done this part up to adding two winding non-linear transformer. In the next case, we are going, and we have also discussed it, enable simulate saturation, simulate hysteresis. By clicking it, then we go for power GUI and hysteresis design. We have covered it, right? Now, in the next stage, we are going to model a synchronous generator. Okay, how to model a synchronous generator in MATLAB simulation. So in this also you have seen the three-phase RLC parallel RLC load is there and three-phase VI measurement is there. We just have to connect what? Synchronous machine PU fundamental. Okay, this machine we have to connect, which is working as a generator. So again we go for the same system, file open, chapter 3, and we have start circuit. Okay, and the moment we going for this is how it looks like. Okay, synchronous machine PI fundamental is there. If you double click it, okay, and go for parameters, put down your parameters of your synchronous generator. That is, it is working at 13,800 volt at 60 hertz, and the power it is giving is 100 e to power 6, 100 megawatt. Okay, this is we have given, and if we have connected to this whole system. But the thing we want to develop is this, a synchronous generator and we want to find out what its rotor speed, what its active output power, or reactive output power. We want to check how it is going. So we make another model like this one. Okay, this is the same system in which we have connected a bus selector. Okay, this measurement device, if you double click this bus selector, then this bus selector will show you the amount of signal it is getting from our synchronous generator. It's getting stator current, it is getting DQ component, like I've told you before, that we have to make our three-phase system into two-phase system before. Then we can simulate our machines. So this is the model that is provided by MATLAB itself. But in this also they have developed a DQ model. Okay, and it is also providing a mechanical. In mechanical, we have rotor angle deviation, rotor speed, and similarly we have output active power and output reactive power. So I have selected mechanical rotor speed, output active power, and output reactive power. Based on your requirement, you can choose any parameter from this circuit. Okay, choose it and just select it, and it will come out here. So there are three variables or that reading that we have to find out. So three outputs are coming, and accordingly we have made our scope into input with three. So if you run, we are not going to run it right now because we have to initialize our synchronous generator. Right now we have given power equal to 1 and field voltage equal to 1, right? So next slide, in the our next slide, we are going to initialize our generator. Okay, this is only a single machine system right now. Okay, because we have synchronous machine PU fundamental, right? So in this, this is a generator system in which we are going to initialize the parameter of synchronous generator. Okay, this synchronous machine. So what we do, we go for continuous power GUI. Okay, we go in tools and then go for machine initialization. Okay, because for one electrical system and two electrical system, that means one generator system, two generator system, we go for machine initialization. But if we go for more than two, we have to go for load flow. Okay, in the load flow they will provide the parameters to our generator, to our load or a synchronous machine that we are going to connect in the our upcoming slides. So right now we only have synchronous machine PU, so we are going for machine initialization. There is
only up to the level of 2 we require this.
We require machine
More than
initialization.
2, we have to go for the
Load flow studies, because for two system this this machine initialization circuit will provide faster way of getting output. But if we go for more than two, then we go for load flow because that will provide more faster way of producing result. Okay, we need accurate and fast result, so that's why we go for two system. One system, that is machine initialization for two generating station.
That is for slack bus. And the load flow means
Swing bus and yeah, right. Okay, so in this we have only synchronous machine PU fundamental. As you select this, then we go for swing bus because there is only one present. So in the swing bus we have to provide a terminal voltage V, RMS and active power. We are providing it. Okay, that much power it's delivering. Okay, and in the three-phase RLC load, we have shown that active power is 40 megawatt and reactive power is 15 megawatt. Okay, in this system, if we go for tools and machine initialization, we just have to provide 13,800 volt terminal voltage and the active power gas, because our output load is of 40 megawatt. So we are giving 40 megawatt to our active gas. And what we do is compute and apply. The moment you compute and apply, these parameters, the constant parameter changes. First was 1 and 1. Now it's come out to be 0.40052 and 1.26909. As per the load requirement, our input setting of a synchronous generator is also changing. So machine initialization will what it do? It will provide the initial values to a synchronous generator. So this is the thing we are going.
It's already being excited in this.
Yes.
It is in the excited state.
In the
Then
excited
it will give
state.
the power out.
Huh. And then you update it. The moment you update it and run it now. So this is the thing that is coming. The rotor speed is decreasing with respect to time, and how the active and reactive power are constant up to the requirement, because what's the value of our megawatt rating was 40, right, and that is 0.15, so it's giving that much, but it is giving in per unit, so zero point 0.4 and 0.15 it's giving. So we have seen how to initialize our generator system. The next one is if we want to connect our grid, whole system connecting to the grid. So we have a one per unit machine fundamental, and we have a three-phase source also there. Okay, we are taking, if we are connecting a three-phase source, this three-phase source will act as swing bus or slack bus. Okay, and then we can select this synchronous machine PU fundamental as PQ bus or PV bus with respect to our requirement. And in this we have connected a three-phase parallel RLC load along with three-phase resistor load. Okay, the load of the three-phase parallel RLC load of 25 megawatt and three-phase parallel RLC RL load of 40 megawatt active power and 15 megawatt 15 MVR reactive power. So this slack bus and this synchronous generator should provide these values to this circuit. So again, file open grid. So this is the system we have created. We have already made this system, right? Synchronous generator to load. We just have connected another three-phase source. Okay. What we want to make is an infinite bus, right? What is a grid? It's an infinite bus, right? So we are going to make a system where there are one or two and more than two sources, and there are two to three or more than three loads. Okay, if we make this system, that means we are making a grid. Okay, so this is a system we are making a grid in which we have connected a three-phase source. In this system, if we double click it, this is 13800 volt, and this in this we am specifying a short circuit level parameters. Okay, because in the grid system we have short circuit parameters that we have to define for our uh, generating station also. So it has provided that is 100 megawatt is the VA present, and 13800 volt, that is the voltage present in our three-phase source, and X by R ratio is 7. So this is the system we have made. And if you go for the load flow here, this is a swing bus. It will automatically take it as swing bus. Similarly, because we have connected only two, all right, so we again go for continuous, tools, and machine initialization. Okay, in this we have synchronous machine PU fundamental, and we have taken it as P and Q generator system. Okay, in the generating station we have known it, the one is the swing bus, then is the PV bus, and then is the PQ bus. So we are already defining the P and Q value for this synchronous machine. Okay, so we have that 65 megawatt is the power that is going to deliver maximum to maximum, and the reactive power is going to deliver is 15 megawatt MVR, sorry, 15 MVR. So if you compute and apply, okay, it will give its value to these constants. Okay, and if you run it again, because we are running for the 10 seconds, it will take some time. If we go for 0.1 second, it will take very less time. Then according to this, we have to change our configuration parameters. If we model configuration parameters is there, and just change the solver here. Okay. Variable step, it is already have taken the ODI to TB step. Is this solver is already providing the best result for this complex system. Okay, and it is already faster than the other solvers. So this is the our generator whose speed is, we are saying the rotor speed is moving varying variable speed we are getting, and similarly the output active power and reactive power is delivering is around 0.65 and 0.15, okay, per unit. And similarly this is the voltage and current we are getting from our synchronous generator. We can also find the amount of power that is delivered by our three-phase source, and in this we have connected a power three-phase instantaneous power block and then connected to the grid power. So if we double click it, as you can see, our grid power, the three-phase source is providing around 0 to 100 watt, and the reactive power it's delivering is about 0, because all the power that is that we need to give to our loads are provided by synchronous system or synchronous machine system. So it's providing less power and reactive power to our loads. So if we go for now a synchronous machine system, okay. So we have already covered that electrical power source. We have to enable specify the short circuit level parameter in which we have to provide face-to-face base voltage, base VA and X. Similarly, in the power GUI block, we are going for machine initialization and we are going for machine list. In the machine list, we are checking the bus type should be a PQ generator type. And then we have to specify active power and reactive power in that circuit. So in this, next thing is adding an induction motor. As you've seen in this, we are adding an asynchronous type machine PU system, right? We are making a three-phase RLC load and we are connecting it with the three-phase transformer. This is the host system in which we are connecting a connecting a synchronous machine along with the three-phase load. So in this we are going to specify that we are using the transformer. So the transformer will be of 13.8 to 2400 kilowatt, 2400 volt. Okay, that type of transformer we will be using. The load will be of also 2400 volt. Okay, so again going to this system. Motor. So this is the system we are connecting. Okay, in this we have connected a three-phase transformer with two winding and a asynchronous machine PU. Okay, because now we have more than two system, two generating units are there, one asynchronous machine are there. So in order to initialize these three, all right, we going for load flow rather than machine initialization. So again, in this circuit, if you check this, the parallel R branch, okay, is of 25 megawatt type, but it's a voltage of 2400 volt because we have connected a transformer parameters 13.8 kilovolt to 2400 volt type. So similarly, these parameters are also 2400 volt and 25 megawatt type. So as you will see, this machine required 25 megawatt. This RL load, this R load provide 25 megawatt. This RLC load provide needs 40 megawatt and 15 MVR reactive power. Okay, so all these values should be provided by these two parameters. Okay, so if we go for continuous PVR jog, so first of all, what we have to do is make this system in the load flow, make it PQ bus. All right, synchronous machine PU system, because this three-phase source will act as a swing bus always. Okay, and then we make this synchronous machine PU fundamental. In the load flow, we will provide generator type is PQ. Then we will provide the active power generation is 75 megawatt, and reactive power it can provide up to infinity. Okay, that we have given. In the similarly, in this case, in the load flow, we have given the mechanical power is 25 megawatt that is required, and in this load flow is swing bus. So if we go for continuous power GUI and go in tools and load flow, okay. So here, this is the whole system. If we compute it, okay, we have to click on the compute, and you will see the asynchronous machine required 25 megawatt. Okay, RLC load required 25 megawatt. SM, that synchronous machine, is providing 75 megawatt and 25 MVAR reactive power. RLC load is of 40 megawatt and 15 MVAR, and this is our voltage source. Okay, and how much power it's delivering, because P and Q is not defined for swing bus, right? So this load flow is actually calculating the amount of power that is delivered by the swing bus, the SM, and how much power it is giving to the loads. So as you can see, the amount of power ASM is getting is 26 megawatt and 19.37 MVAR. Okay. Similarly, our RLC load 40 and 40 megawatt and 15 MVAR is required, and our synchronous machine is providing 75 megawatt power, active power, and 25 MVAR reactive power. It's showing it's there. Okay. Similarly, the swing bus is how much providing? Swing bus is providing 18 megawatt. Okay. Right now, it's not given in there where we have put the parameters. The swing bus is of how much megawatt or how much reactive power it's giving. We didn't know, right? So, and by computing it, we have actually shown that the swing bus is providing 18 megawatt active power and 11.87 reactive power to the whole system. Okay, if you add up, it will come out to be the amount of reactive power that is needed by asynchronous motor as well as by RLC load Z. Okay, then you apply to the model. After computing, apply it to the model and then run the whole system again. So this is the motor parameters. Only speed is there. Okay, so it's around 0.97655. Okay, this and this is the output active power and reactive power provided by the synchronous machine and its speed, how it's varying with respect to load, and similarly the amount of power that is delivered by our swing bus, this much. As you have already know, 19 megawatt is provided by active power is given by our swing bus, so it's coming around 19, right? 19 megawatt is coming around, and similarly how much reactive power? 11 reactive power, 11 MVR, mega MVR, so it's coming around 11.8 MVR, right? So this is showing the exact result that is coming in our circuit. So load flow analysis, by doing the load flow analysis, the whole circuit will initialize in a faster way. Okay. So
If we have a single machine, we can go directly to the load flow analysis or
go for machine initialization. You can go for load flow, but अब वही है ना कि कहते थे कि हथौड़े से काम चल रहा है और आप क्रेन उठा के ले आए, वो यही बात हमारी होती है ना ज्यादातर, तो वही सिस्टम है यहाँ पर भी. So the next thing is we're going to discuss is converting DC to AC inverter with PWM generator. So in this we have used a universal bridge. A universal bridge is a simple bridge circuit, three-phase bridge circuit, which are utilizing 6 switches. So we have given a PWM generator with 6 pulses to this our universal bridge circuit, and this we have taken a DC voltage source. Rather than taking a DC voltage source, you can also take PV cell system with boost converter, and also you can use EV system or wind generation system or fuel system. Okay, fuel cells you can use. You can apply anything here. Okay, I'm not connecting it that because they are all what are they doing? They're giving a DC voltage. So in the hybrid system where you're connecting your PV system, fuel cell, and wind energy system at the DC link, they are giving the constant DC output. Okay, so that system is different. Okay, and this system is different. Okay, you have to just connect it. Okay, so in this we have taken the series RLC load and universal bridge and three-phase VI measurement device. Okay, and in this we are taking a DC voltage source of 900 volt. The universal bridge is of IGBT diode type, and the R load is of 600 voltage, and active power required by it is 1 megawatt. Similarly, the PWM generator 2 level is of carrier frequency 3000 type. You can change your carrier frequency up to your design. Okay, and in this you have to let me show you something first. This is the system. If you write PWM generator here, 2 level type. Okay, this is how it actually looks like. Because it's required an input, एक reference value उसके पास आनी चाहिए जिसके ऊपर वो compare करके करेगा. But if you don't want to give the reference value, so what you have to do, double click it. Okay, and this internal generation of reference signal is there. Just click it. Okay, and provide the modulation index 0.75 or according to your design कि मेरा modulation index इतना होगा और इतनी ये wave generate करेगा. ठीक है, जब आप ये करेंगे तो ये सर्किट कुछ इस तरह से लगेगा फिर. ठीक है, now it providing a PWM signal which is required by our IGBT system. So this is a simple circuit. Okay, universal bridge, as you know, just type universal bridge. Okay, this is a universal bridge. It's different from this. Okay, the same universal bridge can be used for rectifier purposes also. Okay, but we are doing what we are doing right now. We are making an inverter system. So this system has to change a little bit. Just press Control I. Click it and Control I. This is for इन्वर्टर, राइट. डीसी सोर्स को लेना है, थ्री फेज को सिस्टम बनाना है. ओके, अगर आपको इसको रेक्टिफायर लेना है तो आप क्या करोगे, जस्ट मेक इट दिस वन. थ्री फेज सप्लाई इट विल टेक ABC and it will provide DC voltage. Output will be there. So you can make the same universal base system into inverter system and into a rectifier system. Okay, if you double click it, then there is a circuit that power electronic device. Okay, here it is using thyristor that uses IGBT diodes, so it will somehow look like this same one. And if you want to make a rectifier, just use diodes. It will look like this. Right, the same system can be used for as a rectifier and also inverter. Easy, right? So if you run it, this is how it actually looks like. Okay, you can see the blue, orange, and yellow, right? If you see it, it's not a good waveform, but it's still giving a sinusoidal type, little bit sinusoidal type, right? Very little sinusoidal type because it's connect and it's having way too much harmonics. If you want to check how many harmonics is present in this, so first of all, go for scope, configuration properties, logging, log data to workspace. If you go for load data to workspace, then it go ask you variable name, and the save format should be in structure with time. Okay, apply it and okay it. So then go for Power GUI because inverter circuit requires switching. Okay, for for this purpose only we go for discrete type solver in Power GUI. As you can see in the simulation type solver, simulation type, we first were going for continuous type, right? In all the previous example we are going for continuous type, but the moment we came for switching devices or our inverter circuit, we are going for discrete type because it's providing good results. Okay, in the toolbox go for load flow, sorry, go for FFT analysis in this because you want to check how many harmonics are present in this signal, right? So go for this circuit. So what is showing, the scope data was the parameter that we have given to our workspace in the scope system, and the input is variable V, and that in input we have three different waveforms, VA, VB, VC, right? So the signal is 1, 2, 3. So we are calculating for 1. If you want to calculate your harmonics present in the signal, don't go for one cycle. Okay, go for 5 or more than 5 cycles. Okay, we have taken 5, and the maximum frequency preference should be more than, we have taken 10,000 because our signal carrier frequency is 3,000. So we are going to calculate what the harmonics present at 3,000, 6,000, 9,000. Okay, so we are going for 10,000 and then we are going for display. So as you can see in this circuit, inverter circuit, the amount of THD present is 98%. So it's not giving a good waveform. So if we want to make a better inverter system, either go for multi-line inverter system or you can go for filter circuits. Okay, so next we are going to check the filter circuit. This one. So in this we have connected an LC filter. The first configuration was that what, DC voltage source, IGBT, then VI measurement, and three-phase series RLC. Now we have connected an LC filter at the output of inverter. What is there in this system? There is an L branch and a C branch, three-phase L branch and three-phase C branch, which is making our LC filter. Okay, in this system, after connecting this, I have made a subsystem. Okay, a subsystem is what, if you select all this system, okay, and then right click it, here is create subsystem from selection. Okay, the moment you click this, it will make a circuit like this. Okay, this is the circuit present in our system, right? And this is the system, but can I've chosen that system like this and then said create subsystem, and this is how it will look like. Then change the name according to a way, it's the LC filter or RC filter, check it. Okay, and then run this. In this we also check that let's, the scope should have the logging and it's have log data to workspace should be click over here, and the variable name should be given scope data, and the save format structure with time should be given. Okay, we have to check this thing, and then we run this program and again go for F15 analysis. So how many harmonics are present in this system? So the system is actually looking like this. Okay, the waveform is somewhat sinusoidal, right? By applying the LC filter, our waveform has improved. So again, in this system, voltage is there, signal is giving 1, and we have to give number of cycles 5, maximum frequency should be 10,000, and then display. So as you can see, the harmonics present in this signal is 7.60%. In the previous case, it was 98%, right? By using the LC filter, we have reduced it to 7.6%. Okay, but what's the main advantage in MATLAB? We can take any value of L and C, which is not the practical case, right? So we have to go for multi-line inverter circuit and then apply the filter circuit. Okay, because after applying the multi-line inverter circuit, the number of harmonics present in the output of inverter will be around 12%, 11% if we go for 11 level type. At that point of time, the amount of harmonics present is only of 11 or 13 type, highest frequency that is present in that signal. So the filter circuit requirement for L and C will be reduced. Okay, those equipment we can get and make an easy filter, very cheap filter we can get. So this is how we make this whole system, in which we have uses a filter circuit and how can we calculate the number of harmonics present in that signal. Next thing is inverter with LC filters is also there. We have log data to workspace. All the commands that you need I have provided in the presentation. Okay, the steps you have to take. In this, we are going to create a rectifier system. Now we have make, what did we have make? We have made LGBT inverters along with the RLC load. Now we are connecting this system with the diode rectifier and providing to our load system. Okay. So again, going for this circuit, open rectifier. Okay, this is the system we have created. Just I have shown you, in order to make a diode rectifier that, like this type, you use universal bridge and make use of diodes. Like double click it. This is a universal bridge. Okay, and in this power electron device should be diode type. Last time we have used an IGBT type, right? IGBT diodes. In this we are using diode type because in the diode you don't require gate pulses. So it's a simple rectifier system. So, and then you can provide the inductor and the load. This is similar circuit like this system. Just use the parallel RLC branch or parallel or series RLC branch in order to connect this whole system. Okay, if you run this program again, you will see this this LC, this inductor and this load will be providing a filter. Means it will reducing what the ripples present in our signals, because as you already know, in the all the rectifier present in our system, they will give you a ripple output, not pure DC, right? So we are connecting a filter circuit here with inductor and RC, and it will give us almost constant DC. Okay, it will providing us almost constant, because in this you can also see there are ripples present, but it's the amount is very less. Okay, so this is how you will make a diode rectifier circuit. Now in this, the last thing that we have to do is in this is three-phase PI section line. In the grid system, we have transmission lines, right? So in the transmission lines, we have to give what we have to give is what's the R value, what's the inductance value, okay, how much length it is, what's the power required by that line. So this three-phase PI section line is provided between inverter circuit and rectifier circuit. That means our inverter is present at somewhere 5 kilometer or 10 kilometer distance. So we are providing what a three-phase PI section line in between this circuit. This this thing is only given because the distance between the rectifier circuit and inverter circuit is very long. That means 5 kilometer, 10 kilometers. Like you are sitting here and you want to operate a circuit in sector 29. Okay, at that point of time you need lines, transmission lines or distribution lines. So this three-phase PI section line will be providing the parameters for those lines. Okay, so again we open circuit. This is the circuit in which we are providing three-phase pi section. In the pi section, we are providing the 60 hertz frequency, and we are providing inductance value, resistance value, and capacitance value present in this pi section line. And we are given the line length is 5 kilometer. According to your requirement, if the line length is 10 kilometer, these values will also change, right? So if you want to design any circuit or grid system, just go for what are the parameters that is required by that system and just put it here. And this is what a transmission line look like, a grid system, how it will look like. Okay, so we are going to stop here. We are going to stop here. These are the parameters that you have to give by your side, and then these are the blocks that we have used in the circuits, all these circuits, and along with their path in the simulation library. Okay, just check it here and you will get the blocks. Otherwise, if you don't have 2016 MATLAB 2016, because in the MATLAB 2016 you just have to type in the empty space, make a new model, type it, and it will come, the block will come. Okay, so these are the all the elements that is present in the system. The second one is this, and the third one is this. Any question, please? Because I really want to tell you how we work in the MATLAB simulation. Uh, I think did any teacher told you how to use this circuit MATLAB like this?
During this course, it is not.
Because this is the only yes, in the Saturday program they have shown that MATLAB simulation will be there. So I wanted to show you that how we work in the MATLAB simulation, how we connect this electrical system and make inverter circuit or rectifier circuit, and how to connect it with the grid system. So in this we have already discussed how to make a three-phase system, then how to make a three-phase system with synchronous generator source, or how to connect asynchronous motors loads or RLC load or R load. Okay, and then we have made inverter circuit and rectifier circuit and connected with our transmission line pi section, right? So this is the whole system. And if we want to make an electrical system where we want to connect a DC system like PV, wind energy system, fuel cell, and electric vehicles to the grid, what you need requirement is you need a chopper circuit. Ma'am already told you how to make a chopper circuit, then inverter circuit. In between, there is a transmission line parameters you have to provide. Okay, so in this system, I have given you up to inverter circuit. Okay, after that, you need a DC chopper circuit and a DC source like PV and that. So if you go to your home or colleges, just try to develop a circuit in which you are needed a battery circuit or electric vehicles, or you are giving a standalone PV system and connecting it to the whole system. Because I've already shown you up to the inverter parts. So at that point, rather than using the DC voltage source, you can use that system with boost inverter, boost chopper circuit, and PV cells, wind energy system, and fuel cell. So, so that will be your work in the future. So this is the system, and thank you very much.